Continuing with the discussion on chemical properties and reactions of alkanes, the present lecture covers mechanism of free radical halogenation, orientation, reactivity and selectivity.
We have discussed in previous episode about the chemical properties and physical properties of alkanes, which contains boiling point, melting point, conductivity, solubility, along with halogenation, sulfonation, nitration, uh, cracking and pyrolysis, etc. Today in this episode we will discuss about the mechanism of free radical halogenation, orientation in alkanes, conformation of alkanes and reactivity and selectivity regarding alkanes. So, first we will discuss the mechanism of free radical halogenation, that is initiation. The reaction begins with an initiation step, the separation of the halide into two free radicals by the addition of UV light through homolytic cleavage. As we are seeing that this chlorine molecule made up by the covalent bond, or you may say that by the sharing of two electrons of outermost orbit, got cleaved by using this light and two chloride free radicals obtained by this reaction. The covalent bond between the two hydrogen atoms, that is XX, is an electron pair. When the bond breaks homolytically, undergoes homolysis, each hydrogen atom retains one of the two electrons in that bond. Now, we will discuss the propagation step, that is the second step. The initiation step is immediately followed by the propagation step. In this structure, the chlorine free radical combines with the liberated hydrogen free radical to form hydrogen chloride and a methyl free radical. This is called propagation step, a step in which both a product and a reactive species keeps the reaction going are formed. A second propagation step is possible. In this step, a methyl free radical reacts with a chlorine molecule to form chloromethane and chlorine free radical. Now, we are going towards termination step, that is the step 3. A methyl free radical reacts with a chlorine free radical to form chloromethane, that is the product, ultimate product. So, in this structure we are seeing that this chloride free radical is reacting with this methyl group and we are getting this chloromethane. Two methyl free radicals react to form methane, means in previous step we got this methyl radical which combines with another methyl radical and we get ethane. So, when a reaction occurs between free radicals, a product forms, but no new free radicals are formed. This type of reaction is called termination step because it tends to end the reaction. Two chlorine free radicals react to form chlorine molecule. Here we are seeing in this figure that this is the one free radical and this one is the another free radical. When combined together, then we are getting this chlorine molecule, which is not a free radical. So, to summarize, this free radical chain reaction initially contains few free radicals. As the reaction proceeds, the number of free radicals increases and the number of reactant molecules decreases. At this stage of the overall reaction, termination steps become the predominant reactions. The formation of the products takes only in microseconds. Now, we will discuss the orientation. Alkane, a molecule, by looking down a carbon-carbon bond axis showing the relative orientation of groups of the two carbon atoms is known as orientation. Means, if we are saying that this is the first carbon atom and this one is the another carbon atom, when these both joined by this single covalent bond, then these are the four groups, or you may say that these are the four different hydrogen atoms. So, when the orientation takes place of this these hydrogen atoms, then we may say that that is the orientation process, and by the rotation of these hydrogen atoms by using different angles, various forms we can get, that is like antiform, like Gauche form, like staggered form. So, these projections known as Newman projections. Now, various conformations can be represented by using dash wedge notation In a structural perspective drawing, an alternate depiction is a Newman projection. To visualizing the conformation, we use wedges to denote bonds that are extending out from the plane of the page toward the reader, and dashes to indicate bonds that are going into the plane of the page away from the reader. This notation is frequently used to represent the tetrahedral geometry of sp3 hybridized carbons. So, in this figure we are seeing, as we have discussed previously by using our hands, that the circle in the Newman projections, here this is the circle, represents the atoms in front of the bond, and the lines radiating from the center are the bonds of the atom. The bonds of the rear atom emerge from the side of the circle. So, this is the rear hydrogen, and this is the front hydrogen, and this is also the front carbon, and this is the side from which we are using look down this bond. So, now it is of various types. The exact 3-dimensional shape of a molecule at any given instant, assuming that rotation is around single bond. First, we must have to know that what is Newman projection. It indicates stereochemical relationships between substituent groups on neighboring carbons. The carbon-carbon bond is viewed end on, and the carbons are linked by a circle. Bonds radiating from the center of the circle are attached to the front carbon, and bonds radiating from the edge of the circle are attached to the rear carbon. Now, we will discuss the antiform. It is the geometric arrangement of carbon-carbon single bond having two largest substituents at 180 degree apart. Now, another form in conformation is used to be antiform. In this, the geometrical arrangement carbon-carbon single bond, that is, it is the carbon 1 of frontal view, and this one is the another carbon. When joined by this single bond, then the two largest substituents at 180 degrees apart. Say, if these are the two largest substituents and which are having 180 degree like this. So, it is indicating that these are the antiforms which are to be used in conformation of single bonded carbon atoms. Now, we will discuss the antiform which is to be used under conformation. In this geometrical arrangement, the carbon-carbon single bonds means these are the carbon atoms which are joined by this single bond and having the two substituents at different angles. When the angle becomes 180 degree apart like this, and these are the two different substituents having 180 degree apart, then this form is known as antiform. Now, we will use eclipsed form. In this form, the geometrical arrangement around carbon-carbon single bonds in which the bonds to substituents on one carbon are parallel to the bonds of substituents on neighboring carbon atoms is known as eclipsed form. Means that further we are using the same structure. This is the carbon-carbon single bond, and when these substituent hydrogen atoms eclipse to each other, means frontal view we are seeing just only 4 carbon atoms, means these are the behind the frontal view. So, this is known as the eclipsed form. Now, we will discuss Guche form. In this, the conformation of butane in which the two methyl groups lie 60 degrees apart as viewed in the Newman projection. In the eclipsed conformation, the carbon hydrogen bonds on the front, these are the frontal hydrogen atoms, and back carbons are aligned with each other with dihedral angles of 0 degrees, means these are the back side hydrogens and having 0 degree angle of rotation. In the staggered conformation, the carbon hydrogen bonds on the rear carbon lie between those on the front carbon with dihedral angle of 60 degrees, means this is the front hydrogen atoms which are joined by a carbon atom, and these are the back side hydrogens which are further joined by the another carbon atom and having in frontal and rear hydrogen atom the 60 degree angle. In ethane, the eclipsed conformations are higher energy than the staggered. A space filling representation of this conformation shows that the methyl groups are physically touching, leading to the high energy. Now, here we are further seeing that the angle in between rear and frontal view of hydrogen atoms, or you may say the carbon atoms, is 60 degree. So, conformations are different forms of a molecule related by simple rotation about a single bond. Such interconversions are usually very rapid. Now, we will study the conformation of propane. Propane, that is C3H8, is the next member of the alkane family. Conceptually, propane can be viewed as ethane with one methyl substituent. The Newman projections show that propane has a set of eclipsed and staggered conformations similar to the ethane, but with a torsional strain of 3.3 kilocalorie per mole. This strain originates due to the difference in bond angles. So, each eclipsed conformation now consists of two eclipsed carbon hydrogen bonds and one carbon hydrogen eclipsed with a carbon methyl bond. Here we are seeing that this carbon is joined by this methyl group and these two hydrogen atoms, and the backside carbon is bonded by three different hydrogens, and the angle in between backside hydrogen and front side methyl group is 60 degree in staggered form. Now, this is the eclipsed form in which the angle in between these CH3 and this hydrogen atom is 0. So, here hydrogen methyl eclipsing slightly worse than hydrogen hydrogen eclipsing, and the energy is plus 3.3 kilocalorie per mole. Now, we will discuss the conformation of butane. Butane, that is C4H10, has many conformations since its dihedral angle could vary across these three carbon carbon bonds. We focus on the central carbon number 2 and carbon number 3 bond and treat the end carbons generally as methyl groups. Conformationally, butane is more complex than ethane or propane. In the most stable conformation, a dihedral angle is of 180 degree. This particular staggered conformation is called anti. The other staggered conformation has a methyl-methyl dihedral angle of 60 degree and is called Guche, which is less stable. Now, here we are seeing that this methyl group and this methyl group having the bond angle of 180 degree. It is far apart, that is at the top, and another methyl group is at the bottom. Now, that is the Guche form having 60 degree angle in between two methyl groups. So, Guche butane steric interactions. Now, this conformation will be maximum staggered, most stable, and is called anti or trans conformation. Other conformations can be obtained by rotating one of the carbon number 2 or carbon number 3 carbon atoms, though an angle of 60 degree as shown ahead. Now, we will discuss the different bond angles in different types of conformations of butane by using Newman projections of butane. So, in this Guche form, that is also known as staggered form, containing the dihedral angle in between these methyl groups is of 300 degree, and in this eclipsed form the angle is of 240 degrees, and in this anti form the dihedral angle is of 180 degree. This is to be clear. And now, in this eclipsed form we are seeing that the angle is of 120 degree, and in this Guche form, that is another staggered form having the 60 degree in between these two methyl groups, and in this syn or eclipsed form we are seeing that the bond angle, or you may say the dihedral angle, is of 0 degree or 360 degrees. So, that is the nutshell about the dihedral bond angles in between the butane carbon atoms and hydrogen atoms. Now, if we will discuss the stability of the conformation, then we will found that the anti form is highly stable than its Q or Guche form, which is further highly stable than eclipsed, and eclipsed is further highly stable than fully eclipsed. So, this is the scenario of stability of butane conformations. Now, we will discuss the potential energies of butane based on the dihedral angle. So, first we must have to know that what is the potential energy. So, it is the energy which lie in between the position of an object or the position of a molecule. When the dihedral angle is 0 degree or 360 degree, then known as syn conformation in butane, the two methyl groups are in close proximity with the molecule. Therefore, the potential energy is at its highest. When the dihedral angle is of 60 degree or 300 degree, that is known as Gauche conformation in butane, the methyl groups farther apart and therefore, the potential energy drops by 4.1 kilocalorie per mole. When the dihedral angle is 120 degree or 240 degree, that is known as eclipse conformation, butane having a higher potential energy than the Gauche conformation, though still having a lower potential energy than the syn conformation, that is dihedral angle of 0 degree or 160 degree. Anti conformation, when the dihedral angle is of 180 degree, the potential energy is at the lowest, therefore, the most stable, because these are far apart. So, we may say that is very stable conformation. These are unstable because of repulsion, these are less stable than anti conformation. Conformation fourth is also eclipsed and it is least stable, because if we are using eclipsed form, then the energy difference is minimum. So, due to the force of repulsion, these are less stable, and if we are using the anti forms, then the both atoms are far apart and having less repulsive force. So, highly stable. This is because of repulsion between methyl groups which are very close together. It is called fully eclipsed conformation. Now, we will discuss the reactivity and selectivity of alkanes. When alkanes larger than ethane are halogenated, isomeric products are formed. Thus, chlorination of propane gives both 1 chloropropane and 2 chloropropane as monochlorinated products, means single chlorine atom will attach to the alkane, and the halogenation of propane discloses an interesting feature of these reactions. All the hydrogens in a complex alkane do not exhibit equal reactivity. For example, propane has 8 hydrogens, 6 of them being structurally equivalent primary and the other 2 being secondary. If all these hydrogen atoms were equally reactive, halogenation should give 3:1 ratio of 1 halopropane to 2 halopropane monohalogenated products, reflecting the primary secondary numbers. So, light induced gas phase chlorination at 25 degree centigrade gives 45% 1 chloropropane and 55% 2 chloropropane. Here we are seeing a little bit difference in between the productivity, that is 1 chloropropane is of 45% and 2 chloropropane is of 55%. According to reactivity and selectivity principle, the greater the reactivity of a species, less will be the selectivity of a species. Here we are seeing that in this equation, this CH3, CH2, CH3 when react with this chlorine molecule, we are getting 45% 1 chloropropane and 55% 2 chloropropane. Here this chloride atom attached with this second number of carbon atom. So, here is a difference due to the reactivity and selectivity process. The results of bromination, that is light induced as 25 degrees Celsius, are even more surprising, with 2 bromopropane accounting for 97% of the monobromo product. Here in this reaction, we are seeing that this CH3, CH2, CH3 when react with this bromine molecule, only 3% of 1 bromopropane we get, and a huge amount, that is 97% of 2 bromopropane we are getting. So, it is also due to the reactivity and selectivity process of alkanes. These results suggest strongly that secondary hydrogens are inherently more reactive than primary hydrogens. Thus, light induced chlorination of 2 methyl propane gave predominantly 65% 2 chloro 2 methyl propane. The substitution product of the sole tertiary hydrogen despite the presence of 9 primary hydrogen in the molecule. Here we are seeing that this 2 methyl propane, when reacting with this chlorine molecule, we are getting 65% of 2 chloro 2 methyl propane, and rest of the product is just only of 35%. since the hydrogen and halogen product is common to all possible reactions. Differences in reactivity can only be attributed to differences in carbon hydrogen bond dissociation energies required to break a bond homolytically for various kinds of carbon hydrogen bonds. These values are given in the following tables, as we are seeing that this is the bond dissociation energy in kilocalorie per mole, and in methyl, ethyl, isopropyl and tertiary butyl we are seeing that a downfall is going on, that is methyl having bond dissociation energy 103, ethyl having bond dissociation energy 98 kilocalorie per mole, isopropyl is of 95 kilocalorie per mole and tertiary butyl 93 kilocalorie per mole. That is the little bit idea about the bond dissociation energy which is to be used in alkanes. By this reasoning, we would expect benzylic and allylic sites to be exceptionally reactive in free radical halogenation. The methyl group of toluene is readily chlorinated or brominated in the presence of free radical initiators, usually peroxides, and ethyl benzene is similarly chlorinated at the benzylic location exclusively. So, if we see in the alkene this property of reactivity and selectivity, we get that carbon carbon double bonds add chlorine and bromine rapidly in liquid phase solutions. Free radical substitution reactions of alkenes by these halogens must be carried out in a gas phase or by other halogenating reagents. So, the covalent bond homolysis that define the bond dissociation energies listed above are described by the general equation. Here we are seeing that this alkane when get required energy, then it will convert it into this free radical, that is hydrogen free radical, and this R3C free radical. Since the hydrogen atom is common to all the cases cited here, we can attribute the differences in bond dissociation energies to difference in the stability of alkyl radicals as the carbon substitution changes. So, this leads us to the conclusion that alkyl radical stability increases in the order, that is phenyl is lower than primary, which is further lower than secondary, which is further lower than tertiary, then allyl is similar to benzyl in stability.
With this concluding lecture on alkanes, now I will take up another important class of aliphatic hydrocarbons, that is alkenes. So, in the next 4 lectures, I will mainly explain you about preparation methods of alkenes along with different chemical reactions.